Okay, let's get started. Answer your names, please. Bartram, Blair, Donnelly, Elwell, Levengood, Miller, Sheffield, Sullivan. I think I saw Sullivan online. Yes, Sullivan is here. Tillis, and I see Donnelly online as well. Levengood. All right. So let's talk about chapter 7, which deals with atomic structure. And a couple of things I want to say about this particular chapter. You would have met some of the things that we're about to get into in this chapter, but we're going to get into it a lot deeper. Some of these things are very abstract, very difficult to understand. In fact, when I was a student, I had some challenges understanding the topics that we're about to get into. And that is true for chapter 7 and chapter 8. So I'm going to try to go through these chapters as slowly as possible. If you have any questions, feel free to stop me at any time so that I can go back and explain whatever you may have missed. So we're going to talk about the structure of the atom, and in particular, what we'll be concerned with in this chapter and the next chapter is the electronic structure, how the electrons are arranged in the atom. Now, before, way back in the day, it was believed that small particles like electrons behave in very much the same way as regular sized objects, right? So basically, it was believed that Newtonian laws would govern the behavior of these particles, just as how they govern the behavior of regular sized objects. And then some people did some experiments with light, and that led us to the conclusion that that is not the case, and therefore a new theory was needed in order to explain the behavior of small particles like electrons and so on. So that leads us to what is known as a quantum theory, right? And that theory more accurately represents or shows or explains, I should say, the behavior of these particles, right? So that's basically a broad overview of how we arrive at our current understanding of how electrons behave in atoms. So the first thing we're going to talk about here in this chapter is the discovery of what we know, what we call cathode rays. And basically this guy by the name of Johann Hittorf in 1869, he came up with this experimental setup. So let me describe what's happening here. What we have here is a tube which is evacuated, right? So all the air has been sucked out of it. So basically you have a vacuum inside here. And then at this end of the tube, you have what is known as a cathode, which is attached to the negative part of the electricity source here. And this would be the anode, which is attached to the positive part of the electricity source. And then once the circuit is closed, what was observed was that there was a stream of particles emitted from the cathode traveling along straight lines to the anode, all right? So the first thing that one could conclude about the nature of these particles is that they're negatively charged, because they're leaving the negatively charged electrode and being attracted to the positively charged anode. And as always happens when there's a new discovery made, then all scientists rush towards that discovery and try to find out something new about what was recently discovered, all right? And that happened in this case here. So people start investigating the nature of these particles, and a couple of things was discovered about these particles. One, when they hit the walls, the glass walls of the tube, it causes the glass to fluoresce. Basically, that means it lights up. So apparently, the particles carry some energy, which when it hits the glass, the kinetic energy of the particles, some of it at least, is converted to light energy when it hits the walls of the tube. Another property that was discovered about these particles is that they can be deflected by the presence of both an electric and a magnetic field. And that is demonstrated in this recreation of the setup that I showed you earlier. So this is the cathode, this is the anode. You see the stream of particles moving, but they are bent towards the magnet, which is placed down here. If this magnet was not here, the stream of particles will just simply continue to the anode, all right? So that's another thing that was discovered about these particles, that they cause glass and other material to fluoresce when they impact it, and they also are deflected by the presence of a magnetic or electric field. So this guy, J.J. Thomson, he did some modification to the original setup in an effort to investigate the nature of these particles, right? So just to explain what we have here, this is a schematic representation of his setup. You have the cathode here, which is connected to your electricity source, and the anode here is in the form of this particular cylindrical metal with a slit in the middle of it, right? So basically what will happen is that the cathode rays will emit from a cathode and will head towards the anode, but they're sufficiently energetic to pass through the slit. Another slit here was made just to make sure that the beam is narrow, and then the cathode rays are allowed to pass through this region. Now in this region, we have two plates which are connected to another electricity source. So you have a circuit right here. And basically what these two plates do is that they produce what is called an electric field. So basically you have the cathode rays passing through the electric field. And also you have two magnets here. So therefore there's a magnetic field that is in this region. So basically what he did, J.J. Thomson, what he did was that he played around with adjusting the magnetic and the electric field to see the effect that it would have on the direction of the cathode rays. And as you can see here, by simply adjusting the electric field and the magnetic field, you're going to have the deflection where the cathode rays start moving deflected to a particular angle, and there's a measuring scale here to measure the angle of deflection. All right, so that's the setup, and there are some calculations involved which I won't get into. Maybe when you do physics, you'll get into that. I remember when I did physics back in the day, we actually look at the equations that are involved in this setup, but I'm just going to give you the conclusion of this setup. He concluded, based on the data that he collected from this experiment, was that the mass of the electron, of the particles, which we now know to be electrons, I kind of give it away right now, but the mass of the particles divided by the charge carried by each particle is equal to minus 5.686 times 10 to the minus 12, all right? So basically that's a very important step that was made in the investigation of the nature of cathode rays, all right? So not, of course, the next thing we need to find is, okay, what would be the mass or the charge or both of these particles? So as I said before, we now know these particles to be electrons. So the cathode rays is basically a stream of electrons, all right? So again, as I said before, people try to find out more about the nature of these particles. And this guy here, I think he's from Holland. He came up with his very famous oil drop experiment. And let me kind of describe what's happening in this setup. So you have two plates here, again, connected to an external circuit. So this plate here is negatively charged. So this would serve as the cathode. This plate is positively charged, right? You have an oil here, and I forgot exactly what kind of oil it is. I need to look it up. But basically, you have oil here in this container here. And of course, you have this apparatus here, which allows you to spray the oil in the form of a very fine mist. So you have very fine droplets emanating from the spout right here. You have a hole here in the cathode plate. So you're going to have, from time to time, drops passing through the hole and ending up in this region here. Now, in this region here, we expose the oil to radiation. And the radiation, what the radiation does is that it ionizes the oil drop by simply knocking off electrons from the oil drop. So the oil drop is going to be charged, and depending on the size of the electric field inside this region here, as a result of these two plates, you can actually suspend the oil drop, right? So basically, the oil drop will be suspended between the two plates, and therefore the net force on the oil drop will be zero. What that means is that the gravitational pull, which was responsible for pulling the oil down, would be exactly equal to the electrical field causing the oil drop to, or a force being applied to the oil drop upwards. And based on that balance, again, there are some calculations that can be done, which I won't get into, but based on the data obtained from this experiment, he determined the value of the electron charge. And it turned out that the charge on the electron is minus 1.6 times 10 to the minus 19 coulombs. All right, coulomb is a unit, is the metric unit of charge. So if we know what the charge is and we know what the mass to charge ratio is, then we can simply calculate the mass. So let me just show you something here. Let me squeeze it up here. So the mass to charge ratio was calculated before, and if we multiply that by the charge, which is what this is, then we're going to get the mass. And that's exactly what was done. And based on that calculation, we determined that the mass of the electron is 9.109 times 10 to the minus 31 kilograms. All right. So that's basically how we have determined these values for the electron. All right. Okay. So J.J. Thomson, again, the same guy who made the last setup, well, not the last setup, the one before, where he determined the mass to charge ratio, he came up with a model for the atom, because at that time, everybody was trying to, come up with some way of representing the atom based on experimental data. So this is his model. He basically proposed that the atom consists of a large positively charged sphere, and you have the electrons embedded in it. In some textbooks, they call it the plum pudding model, because, of course, that's basically similar arrangement when it comes to the plum pudding, according to the model that J.J. Thomson came up with. So according to his model, most of the size of the atom is taken up by the nucleus, right? For example, in the case of the hydrogen atom, he suggests that basically there's one electron, right? And embedded in that electron is the, you have a large nucleus, I should say, and embedded in the nucleus, you have the one electron, right? Which would be at the exact center, right? And then he proposed that for the helium atom, you have basically the same situation, excepting that you have two electrons, but those two electrons will be spaced out evenly along a straight line through the center, right? With the electron being halfway between the center and the outer surface of the sphere. So this is basically his model of the helium atom. And if you were to remove an electron from that, then the remaining electron will just simply go to the center according to the plum pudding or raisin pudding model put forward by J.J. Thomson, all right? So, as always happens in science, if somebody comes up with a theory, then maybe that person or somebody else comes up with an experiment to test that theory. And that's exactly what was done by another scientist by the name of Rutherford. So he decided to test this plum pudding model idea with this setup right here. And in this setup, what you have here is a metal foil. And if I remember correctly, it's a gold foil, very thin foil, right? And what we have here is a source of alpha particles. Now, I don't know if you know what alpha particles are, but alpha particles are basically the helium-4 nucleus. All right, in other words, this is the alpha particle right here. Basically the nucleus of the helium atom, all right, without the electrons. So basically there's this radioactive element known as radium, which spontaneously produce these particles. What's that sound? Okay, so what he did was that he allowed the alpha particles to shoot directly at the metal foil. Where's that sound? All right, so that's basically the setup. Now, if the Rutherford model, if the J.J. Thomson model was correct, then if you shoot alpha particles, now remember, according to the model, the atom consists of a large nucleus and the electrons are embedded in it. So if you shoot positively charged particles towards that structure, then because of the fact that the nucleus is large and positive, and you have the alpha particles coming in which are positive, you'd expect that the alpha particles would be repelled, right? because you'd expect that the positive charges would repel each other because they're like charges. What he found instead was that most of the particles will pass right through the metal foil, all right? Which was very surprising given the model that was put forward by J.J. Thomson. Now, some of the particles will pass through but be deflected at an angle as shown here and shown here. And then there are some that won't pass through but will be reflected back as shown by this pathway right here, right? So what this shows is that the J.J. Thomson model is not actually consistent with the finding that Rutherford discovered in this experiment. What this seems to suggest otherwise is that the structure of the atom is such that most of the size of the atom is taken up by the electrons, which are small in terms of size. And as far as the nucleus is concerned, the positive part, it will be very small and concentrated in the center of the atom, right? That seems to be a more logical conclusion to come to based on this setup. And in fact, the next slide shows basically why that is so, right? So basically, according to the current model that we use now, the nucleus is here, small, right? Does not take up most of the size of the atom, while the electrons are spread out like this. So that explains why most of the particles, most of the alpha particles will pass right through undeflected, because basically most of the particles will not come into contact with either the electrons or the nucleus. Now, there are some particles that will be deflected, such as the particle that is following path number 3 as shown here, right? You see that? Basically, this particular alpha particle is coming into close proximity to the nucleus and therefore will be deflected at an angle. There are some particles that will come into close proximity to the electrons and be deflected, like as shown here for path number 2. And then there are a few particles that will come into direct contact with the nucleus, as you can see here in path number 4, right? So this model here makes more sense and is more consistent with what was discovered by Rutherford's experiment. And therefore, for that reason, we do not accept the J.J. Thomson model anymore to explain as a model to explain the structure of the atom, all right? So this is yet another important discovery that was made in an effort to understand the structure of the atom. Okay, so we now know that at this stage that there are two types of charges present in the atom. You have the positive charges, which are the protons, and the negative charges, which are the electrons, right? And later on, I would say probably about 2 decades after the discovery made by Rutherford, the neutrons were discovered. The neutrons kind of eluded discovery for quite a while, right? And that's because the neutrons have no charge. So back then, they did not have the technology to discover neutral particles. But there was some suspicion, of course, that there was a third particle, because it was found that when you look at the mass of the protons and the electrons, and you add them up, in some cases, they did not equal to the mass of the atom. So there was some suspicion back then that there must be a third particle. And a guy by the name of Chadwick discovered those particles, which would be the neutrons. And it was discovered to have nearly the same mass as protons and no charge. I won't go into the experiment that he did to discover the neutrons, but basically he discovered it. So as a result of these discoveries, certain terms were introduced, such as the atomic number. Back in the day before then, the atomic number, that term was not in use. Back then, people didn't know about the structure of the atom. So the only number that was used to identify atoms or elements were the atomic mass, right? But since the discovery of the electron, then it was discovered that each element has its own unique number of electrons and protons. Then the term atomic number was introduced, which of course by definition is the number of protons present in the nucleus of an atom of an element. I'm going to skip this. I'm going to leave this for you guys to read upon. I'm quite sure it's in your textbook, mass spectrometry. It talks about a method of separating gaseous ions based on their mass to charge ratio. It's a relatively simple setup. So I'm just going to leave you to read upon that. If you have any questions concerning this, feel free to contact me about that. So let me just move on to wave motion. So you might be wondering, okay, what does this have to do with the structure of atoms? I'm going to make this clear shortly. It's kind of hard for me to set it up, letting you know exactly what is going to happen in this chapter concerning the connection between wave motion and the atomic structure. So what I'm going to do right now is basically talk about wave motion, and then we're going to see the connection to the electronic structure in the atom. Now, I'm quite sure we're familiar with this setup here. I'm quite sure as children, we have played with a rope attached to some fixed object like a wall, and you hold the other end of the rope and you go up and down like this, right? And we all know what's going to happen. You're going to generate a wave along the length of the rope, right? So basically, initially, if you concentrate on one part of the rope like this, then initially the wave will travel so that that particle will go up, reach a maximum point, and then start going down, and then go up and down again, and so on, right? So you're going to generate a wave, right? Our understanding of the nature of waves and certain terms associated with wave motion is going to help us to understand radiation, which we're going to talk about shortly, and that is going to lead to a discussion of the atomic structure, all right? So as far as the nature of the wave is concerned, it is characterized by several terms. One of them would be the height of the crest or the depth of the trough. That is called the amplitude, all right? But there are other particular terms we're going to learn concerning certain, how should I put it, certain aspects of wave motion. Now, as I said before, understanding the nature of wave motion will help us to understand electromagnetic radiation, right? So, which include the light to which our eyes are sensitive to, all right? Now, the origination of electromagnetic waves comes about as a result of the movement of electrical and magnetic fields. And this is basically showing you what we're talking about here. So basically, you have the vibration of the magnetic field represented here in the red or pink line. And then at right angles to it, you have the vibration of the electric field component of the electromagnetic radiation. So basically, you need those two at right angles to each other in order for you to generate an electromagnetic wave, all right? So this is basically true for every form of radiation that we're going to talk about shortly. So, as I said before, there are several things that we need to know about any waveform, which includes electromagnetic radiation. There are certain characteristics associated with them. One of them is what is called the wavelength. The wavelength, by definition, is a distance between two identical points in consecutive cycles, right? And, you know, for the sake of convenience, we can say that the wavelength is a distance between two peaks of the wave, as you can see here, right? And the symbol that is used conventionally to represent the wavelength is this Greek letter lambda, right? Looks like an upside down Y, but it's actually a Greek letter, all right? So basically, that's what the wavelength is. The wavelength is a distance between two successive peaks, or it can be defined as a distance between two successive troughs, all right? Which would be the minimum part of the wave, all right? So that's a wavelength. The other characteristic of waves is what is called the frequency, right? And the frequency, by definition, is a number of cycles of the wave that passes through a point in a unit of time. And the unit of time is usually in seconds, okay? I don't recall ever seeing the unit of time expressed in any other unit for this purpose, except in seconds. Now, I'm sorry, going back to wavelength here, the wavelength here can be expressed in any units, but usually the units would be, for the purpose of our calculations in this course, would be in meters, all right, usually. As far as frequency is concerned, which I just talked about, the unit of frequency would be seconds to the -1. And there's a special name given to that particular unit. It's called the Hertz unit, Hz, spelled H-E-R-T-Z, all right? So whenever you see seconds to the -1, it's the same thing as the Hertz unit, okay? That's a unit of frequency. And then now the amplitude I mentioned before, this is a distance from a line of no disturbance through the center of the wave peak, all right? And that is going to be related to some other aspects of EM radiation that we're going to talk about shortly. Now, there's a relationship between the frequency and the wavelength, as shown here on this slide, right? Oh, I forgot to mention, this here, let me go back here. This here symbol is the symbol that you see in most textbooks to represent frequency. It's a Greek letter. It looks like a V, but it's a Greek letter. It's called nu, all right? So we typically use nu to represent frequency. However, in some textbooks, I've actually seen them use F to represent frequency. So you can use nu or F. To me, it doesn't matter, all right? I typically use nu because that's just something I'm used to, all right? Okay, so as I was saying, there's a relationship between the frequency and the wavelength as shown by this equation, right? The frequency times the wavelength gives you the speed of the wave. Usually, as I said before, the frequency is expressed in seconds to the minus one, seconds to the minus one, and the wavelength is usually expressed in meters. So therefore, the unit of the speed of wave would be ms to the minus one or m over s, all right? So that's basically the relationship between the frequency and the wavelength. And this is true for every single waveform, all right? Let me see here. However, let me just check something here. Okay, so that's the relationship between frequency and wavelength. Now, this here, on this slide, this here is what we call the electromagnetic spectrum. This is a listing of all forms of electromagnetic radiation that exist, and they're placed in this particular chart in order of decreasing frequency going from left to right, all right? That means that going from right to left, the wavelength increases. Going from left to right, the wavelength increases. So I'm going to explain what all that means. But before I do that, let me talk about the different regions of this spectrum here. So at the low end, in terms of the wavelength scale is down here. At the low end, you have what are known as the gamma rays, all right? And then there's some overlap between the gamma rays and the X-rays. And then you have ultraviolet rays, all right? And then now there's a narrow band here, all right? Which is what we call the visible part of the spectrum. And that visible part contains all the colors of light that our eyes can detect, all right? So it starts with violet. Hold on. Well, there's red here. And then you have orange somewhere here. And then yellow somewhere here. And then you have green here. And then you have blue here. And then you have indigo here. And then violet, all right? So that's basically the full spectrum. I use this to remember the order of the colors. Roig-Biv, right? Red, orange, yellow, green, blue, indigo, violet. And this is in order of increasing frequency, all right? So that's the visible part, right? And then you have, oh, and by the way, I remember reading somewhere, I don't know how true, well, I don't know how true it is, but I'm leaning towards believing it, that only women or females can determine the difference between indigo and violet. So I tend to believe that because I don't know the difference between those two. So I have a feeling that that may be true. And then after that region, then you have infrared, then you have microwave, and then you have the different radio frequencies, including those associated with the use of cellular phones. And then you have the extra low frequency radiation, right? And that's a full spectrum. So as you can see from this diagram here, we can only see a very, very, very small part of that entire spectrum, right? And that's, as I said before, the visible part that is indicated right there, all right? Now, one important thing that you need to know about all forms of electromagnetic radiation is that, well, apart from the fact that they all show wave-like motion, one important fact that you need to know is that they all travel at the same speed. All forms of electromagnetic radiation travel at the same speed, and that speed has been determined experimentally to be equal to 3.00 times 10 to the 8 meters per second. Excuse me. All right. That is true for every single form of radiation. All right. So basically what that means is the following. If c is the speed, and remember now, c is equal to lambda times nu, right? The wavelength times the frequency. What that means is that lambda, the wavelength for any radiation, times its frequency is going to be equal to that one value. So what that means, therefore, is that there's an inverse relationship between the frequency of radiation and the wavelength, right? So basically, the longer the wavelength, the smaller the frequency, and vice versa. And that is the reason why, going back to the previous diagram right here, if you look at the scale here, you'll notice that the frequency increases, the frequency decreases going from left to right, but it increases as far as the wavelength is concerned, going from left to right. And that's because you have that inverse relationship between frequency and wavelength. And that is true for all forms of radiation, because when they multiply, you're going to get 3.00 times 10 to the 8 meters per second. All right. Okay, I'm going to stop here for the time being. And I want to focus your attention on the first question first couple of questions. Yes, the first couple of questions in this assignment. And for you guys out there in Zoom, I think, well, I don't know. Let me see if I published it. So let me go here. Let me go here. Let me go here. Files. Segments. Okay, apparently I didn't publish it, so let me do that now. And in fact, let me open it up so we can look at question number 1. Okay, so let's look at question number 1. It says an FM radio station broadcast at 95.5 megahertz, calculate the wavelength of the corresponding radio wave. So let me do this here. Okay, so the equation we're going to use is the equation I showed you earlier, which is C is equal to lambda times nu, right? So we know what C is already. That's always constant. 3.00 times 10 to the 8 meters per second, right? What the question is asking for is the wavelength. So what I would do with this equation is write an expression based on that for the wavelength, and the wavelength is going to be equal to C over nu, the speed of light over the frequency. The speed of light is 3.00 times 10 to the 8 meters per second. Question is, what's the frequency? They gave the frequency as 95.5 megahertz, but we need the frequency to be expressed in hertz, right? So what do we do with that? We have to do a conversion. So 95.5 megahertz, we're going to divide that by, and then we have to convert that megahertz value to hertz. Mega means 10 to the 6 or a million. So therefore we can write as a conversion factor 10 to the 6 hertz above and 1 megahertz below. And that's it. That's the setup. So let me do this calculation here. So this is 3 times 10 to the 8 divided by 95.5 times 10 to the 6. And round off to 3 sig figs. So according to my calculations, this works out to be equal to 3.14 meters. And that's how you do that. Any questions about this one? Any questions? Okay. Is it okay for me to clear this? All right. So let me scroll down to question number 2. Now, the only part of question, let me check something here. Hold on, 2A, 2B. Okay, you won't be able to do the 2B part yet, but you should be able to do the A part for question number 2. It says in question number 2A, the laser in an audio compact display uses light with a wavelength of 7.80 times 10 to the 2 nanometers. Calculate the frequency of this light. So how would you tackle this problem based on what we have done before? What's the question asking for? Question is asking for the frequency. Very good. So how would you go about setting up your equation for that? What's the formula for the frequency? Nu is equal to what? I'm sorry? No, actually it would be the other way around. C divided by the wavelength. Remember, the equation is C is equal to lambda, lambda times nu. That's the equation, right? So nu is what the question is asking for. C is always 3.00 times 10 to the 8 meters per second. And the wavelength is given as 7.80 times 10 to the 2 nanometers. Now, what would be the next step? We'd have to do what? Exactly, you have to convert the nanometers to meters. So how would you do that? What does nano means? What does the prefix nano mean? Nano. You can look it up. It should be in your tables. Nano means what? Nobody knows? One nanometer is equal to what? How many meters? Ten to the minus 9, exactly. Okay, and that's the setup. The nanometers unit will cancel out, the meters will cancel out, so the only unit remaining would be seconds to the minus 1. So let me do that. 3 times 10 to the 8 divided by 7.8 times 10 to the 2. Okay, so according to my calculations, this works out to be equal to 3.85 times 10 to the 14. Seconds to the minus 1. 14. All right? And that's how you do that. Okay, any questions about this? Any questions? Any questions? Any questions? All right, so let me how am I going to do this? Okay, let me clear this and then get out of this and then go back to the PowerPoint. Okay, so now we're going to see, we're going to still get to electronic structure, but there's one more thing we need to discuss here, and that is this whole concept of a continuous spectrum. So what you're looking at here on the screen is a setup which basically splits white light into its individual separate colors. So white light that we can see coming from the sun, for example, is actually a mixture of different colors of light, and we can actually separate that. In fact, in nature, that happens whenever you see the rainbow, right? Basically, what you're observing there is something similar to what we see here, where the sunlight is basically split into lights of a different colors as it passes through the water droplets in the atmosphere. So let me explain what's happening here. You have the white light source, produces white light, which is allowed to pass through the slit. So you're going to end up with a beam, which is allowed to pass through this prism. Now, this prism can be made up of glass or transparent plastic, right? And basically what happens is that when light moves from the regular atmosphere into a medium transparent medium like glass or plastic or even water, the light bends, all right, or the beam bends, right? The term that they use for that is refraction, okay? And it turns out that the different colors of light have different levels of refraction. So it's on the basis of that you have the separation of the different colors of light as it passes through the prism, and then it emerges on the other side and is projected onto a screen, and you end up with what is known as a continuous spectrum, right? And the reason why it's called a continuous spectrum is because as you go from one end to the other of this spectrum, there's no clear line of demarcation between the different colors, right? So the red runs into the orange, which runs into the yellow, which runs into the green, blue, and then so on and so forth, right? So that's basically what we call a continuous spectrum. And the different colors of light, of course, have different wavelengths associated with them. And because the wavelengths are different, the frequencies are different as well. Remember, there's an inverse relationship between the wavelength and the frequency of any form of radiation, all right? So these are the approximate wavelengths for the different colors as shown here. So that's a continuous spectrum. Now, there's another type of spectrum. I'm seeing a weird message coming up on my screen. I don't know what that means. Anyway, there's another type of spectrum known as a line spectrum. And that is different from the continuous spectrum that we just saw. Now, I don't know if you can see it from where you are, but here's the line spectrum for hydrogen. I'm going to explain basically the setup. It's basically the same setup. The only difference is this, that in here, you have a tube of hydrogen at low pressure, right? You have two electrodes at each end of this tube. These are connected, of course, to an external circuit. So when you flip the switch, what happens is that the gas in the tube starts to glow, right? And that light is allowed to pass through the spectrum, through the slit, through the prism, projected onto a screen, and you end up with what is known as a line spectrum. Now, I don't know if you can see it from where you are, but basically in the line spectrum, in this case of hydrogen, you have lines of specific colors, right? So as I said before, I can't tell the difference between indigo and violet. So I'm presuming that one of these is indigo and the other one is violet. This looks blue, this looks red, and that's basically the line spectrum of hydrogen, right? And you can try this with other elements as well, and you're going to get line spectra for those elements, right? As long as you have the gas trapped in a tube under low pressure conditions, and then you subject that to an electrical discharge through an external circuit, right? So that's a line spectrum. And of course, the obvious difference between the line spectrum and the continuous spectrum is that in the continuous spectrum, you have colors from one end to the other. In the case of the line spectrum, you only have lines and you have dark regions in between those lines, all right? So that's basically what the line spectrum looks like in the case of hydrogen. And these are basically line spectra for other elements, all right? And each element has its own unique line spectrum, okay? And this is how, for example, scientists can tell what particular elements are existing in the sun. You know, the astronomers, they have their special instruments that they can look at the radiation coming from the sun. They can identify certain line spectra for certain elements and basically come to the conclusion that those elements are present up there. So it is known, for example, that iron, which is a solid down here on Earth, exists as a gas up there in the sun, all right? So that's the line spectra that is projected or produced by excited elements or atoms of the elements, right? And another term for line spectrum, we call it the atomic emission spectrum for each of these elements. Okay, so we're going to get into shortly, how does that relate to the electronic structure, right? Well, we have some other things that we need to talk about in terms of the quantum theory. Okay, so this guy Planck, he proposed, right, based on some information that he had, that vibrating atoms in a heated solid can only absorb or emit electromagnetic radiation only in discrete amounts, like packets, right? And he came up with a formula, which is right here, and that formula gives you the energy of each packet of energy. The energy of that packet, which is known as a quantum, by the way, is equal to h times nu. Now, we already recognize that nu is a frequency. So what is h? H is known as Planck's constant, and it is given by this value right here. For all purposes, we're just going to round it off to 3 sig figs, right? So 6.63 times 10 to the minus 34. And please note the units. The units is joules second, right? That's a unit of H, Planck's constant, right? So basically what Planck is saying is that when an atom is losing or gaining energy, it only gains or loses discrete amount of energy, and the energy is equal to this formula right here, all right? So basically, according to Planck's quantum hypothesis, the energy that is absorbed or emitted by atoms, heated atoms, can only be absorbed or emitted as whole multiples of a quantum, all right? And this seems to indicate that the radiation in this sort of situation exists as a stream of particles. So that's what Einstein considered. He considered them as little packets, and he called them photons, all right? And the energy of the photon is given by the same formula which I showed you earlier. And there's this experiment right here, which basically gives support to that idea. Let me briefly describe what this experiment is all about. So in this setup, you have a metal here which serves as the anode, and then you have this photoemissive cathode. And basically, both of them are connected to an external circuit. And a part of that external circuit is an instrument here known as an ammeter, which measures the flow of the electric current. And basically what happens is that the photoemissive material basically releases electrons when exposed to light of a particular frequency. So that's what happens here. The light is allowed to shine on the photoemissive cathode. And believe it or not, the electrons that are emitted here will travel through space to get to the anode. And therefore that will be detected as an electric current flowing through the external circuit, all right? Now, one thing about this setup is that it was noticed that only photons with frequency above a particular limit will cause a current flow. In other words, if the radiation is not above that frequency, there's no current that will be flowing. So basically, if you were to graphically represent what we're talking about here, basically, if you have a frequency of radiation anywhere within this region, there'll be no electric current flowing through the external circuit. As soon as you reach a threshold value, then all of a sudden, you're going to get a current flow, all right? So the key thing that is taken away from this experiment is that the flow of the current is not dependent on the intensity of the radiation, which is related to the number of photons. It is dependent only on the frequency and not the number of photons, all right? So that seems to give support to the idea that radiation exists not only, or does not only display wave-like character, but also display particle characters, all right? Okay, so stick a pin. So based on what we have just discussed, you should now be able to do the B part of number 2, as well as number 3 and number 4. All right, so the B part of number 2, number 3, and number 4. In fact, let me help you out with the B part of number 2. So let me okay, what am I doing? What am I doing? Let me see. I'm going to stop sharing for a while, and then let me okay. Now let me go back to sharing. Okay, so the B part says calculate the energy of a single photon of this light. So the formula that I showed you just now for calculating the energy is E is equal to H nu. H is Planck's constant, nu is the frequency. Now, hold on. Did they give the frequency or did we calculate the frequency? Hold on. Oh, we calculated the frequency. So I need you to remind me of what the answer was.
3.85 times 10 to the 4.
So H is 6.63 times 10 to the minus 34 joules second. And what did you say the frequency was?
It was 3.85 times
3.85 times 10 to the 14. Okay. And this will be hertz, which is the same thing as seconds to the minus 1. And that's it. So let's see what that gives. 6.63 times 10 to the minus 34 times 3.85 times 10 to the 14. Okay, so according to my calculations, this works out to be equal to 2.55 times 10 to the minus 19 joules. And that's it. That's all that is done for that one. All right. Okay, let me scroll down to question number 3. Okay, so I don't think you need my help, but you can go ahead and let me clear this here, get this out of the way. Okay, so for question number 3, let me see here. Right, so now you should be able to calculate the frequency and energy of a single photon, and it gives you the wavelength, right? So let's deal with the frequency first. How would you calculate the frequency? What formula would you use? My throat. C is equal to wavelength times nu. And the question is asking for this, right? So what is nu equal to based on this? It would be equal to what? Okay, very good. C divided by lambda. So to calculate nu here, we're going to divide C, which is always 3.00 times 10 to the 8 meters per second, divided by lambda, which is the wavelength. I gave the wavelength as 1.0 centimeters. So what do we need to do to this? All right, so to convert, we're going to need centimeters 10 to the minus 2. So basically 1 meter will be equal to 10 to the minus 2. I'm sorry, I have this backwards. Where is this here? It's going to be 1 centimeter down here and 10 to the minus 2 meters above. So let's see what that gives. So that's 3 times 10 to the 8 divided by 1 times 10 to the minus 2. So the answer I got here is 3.00 times 10 to the 10. And the units here would be seconds to the minus 1. All right. So that answers the first part here, the frequency part, and then to calculate the energy, what's the formula we're going to use for energy? Energy is equal to what? H times nu, right? So in this case, the energy will be equal to 6.63 times 10 to the minus 34 joules second, multiplied by the frequency that we just calculated here, which is 3.00 times 10 to the 10 seconds to the minus 1. So let's see what that gives. Times 6.63 times 10 to the minus 34. Okay, so according to my calculations, I got 1.99 times 10 to the minus 23 joules. Let me do that again just to make sure. I think I may have made an error somewhere. Okay, that's it. 1.99. That's what I got. 1.99 times 10 to the minus 23. All right. Any questions about this? Any questions? Any questions? Okay, now for the B part, it says calculate the energy of an Avogadro's number of these photons. So remember, the energy that we calculated here was just for one photon, right? So to calculate for Avogadro's number, basically all we have to do is multiply Avogadro's number, which is 6.02 times 10 to the 23 photons by 1.99 times 10 to the minus 23 joules per photon. So let's see what that gives. So 6.02 times 10 to the 23 multiplied by 1.99 times 10 to the 23 minus 23. So according to my calculations, I got, okay, I need to round this out to 3 sig figs. So I got 12.0 joules. All right. Any questions? Any questions? Okay, let me clear this. And let me scroll down. Okay, so I want you to try number 4. And if you have any problems, let me know. In the case of number 4, they gave you 2 wavelengths, right? And they're asking for you to calculate the frequencies, the energy of a single photon for each wavelength, and then the amount of energy for 1 mole of photons with each of these wavelengths. And that's it. Okay, I'm going to stop a bit early, because I need to get some ice for the lab coming up. So, we're gonna continue from this, next class. Well, not next class, because the next class you'll be getting your test number 2. So make sure you come prepared for that. And then next week, we will continue from where we left off in lecture. I will only be available for office hours in the morning on Thursday if you need help, because I have class all day tomorrow. We won't have any office hours tomorrow. So if you have any questions about your test, I'll be available upstairs in the morning on Thursday from 8 to 11. All right.